Okay. Um, Hi, folks. I'm Keshav Murthy. Let's get started with the talk. I manage the query processing team within Couchbase. So today I'm going to cover the optimizer details and how to use the features for optimizer to tune your queries. Okay. For those of you who haven't used Nickel, I'll start with a very brief introduction of Nickel. Unlike the 7-hour workshop we had yesterday, it's going to be like a 5-minute introduction to Nickel. And then we followed up that with how to understand the query plan that the Nickel comes up with, and then the background on how we approach the query optimization and all the options that we have, and then finally some more tuning using the indexing features that we have. So let's get started. Okay. So how many of you have used SQL before? Okay, majority of you. How many of you have invented SQL? So we have Don Chamberlain, who invented SQL. I'm glad to have him in the audience. So SQL takes relations as input, and it does the manipulation of this relations, and the result set is another relation. Right? That's what the SQL language does. And there are many beautiful things about SQL. It's declarative, so you tell the system what to do, and the database engine figures out how to implement what you have told it to do, and that's advantage of one of the advantages of SQL. So comparing that to NoSQL systems that are built on the JSON model, the input to any processing is sets of JSON documents, and you want the result to be a set of document. You could have customer information, loyalty information, orders information. You want to manipulate these sets of documents to produce other document required by your business. Without a declarative query language, before you had declarative query language, you had APIs to access individual documents based on the keys, and you fetch all the documents, wrote a program to manipulate them in your application, and produce the resultant document. This was the world for the first few years of NoSQL systems. These programs had to be built manually. They had to be maintained. They had to be checked, debugged. So those are all expensive. Right? It's like having a powerful query engine, but you don't have a way to manipulate the data. You had to write these programs. You had to literally manipulate each of the documents to produce the result. The aim is to get the status back into how relational systems and SQL systems helped you manipulate the data with a clear and easy to use steering wheel. Right? So what Nickel does is to replace those API-based access and complex programs that you had to develop with declarative query language that is very close to SQL. If you know SQL, you can grok what's in Nickel with some of the extensions that we have done to understand and manipulate the JSON data and the flexible schema that comes with JSON. So in summary, the input for Nickel is sets of JSON documents. The result of the processing is a set of JSON documents. So there are several other languages that manipulate JSON, but give you the flat data that works well if you're just doing a basic analysis. But in Nickel, you don't lose the relationship that you have embedded in your JSON documents with objects and arrays and so forth. So that's why there is no impedance mismatch between the input and the output. Input is JSON, output is JSON as well. So the goal of Nickel is to give developers and enterprises an expressive, powerful, and a complete language for querying, transforming, manipulating JSON data. It's not just select statements. We support select, insert, update, upsert, and merge as well. So you can you have the end-to-end language support for all of your application development. In addition, we have infer and explain to understand the data, understand the query plan as well. So here is an example of a query. This looks and feels like SQL, and that's by design, except for the unnest operation. So everything else and the on keys join clause, everything else should look and feel like your SQL. We have the projection clause with customer ID, name, and the aggregation, and the from clause where you specify your key spaces or buckets to select the documents from. And the group by does the same thing as in SQL. It groups by those attributes. Having clauses filter out the result set after the aggregation, order by sorts the data, and limits provides you the pagination. So by design, this is an extension to SQL, so that the familiarity of the people who are familiar with the SQL can grok the nickel and start developing from day one. Okay, so that's the background of SQL. So now let's understand, how Nickel query engine generates the plan, and how to understand the plan, as well as how to improve the query performance by looking at the query plan and doing this work iteratively, right? Let's look at the execution first, and then look at the query plan that results in this execution. Right? So applications, whether through direct REST API or through SDK or through ODBC drivers from Simba and CData, eventually submit the query through the REST API that we have published for query service. So we get the query, we parse, analyze, and create the plan. Right? We first create the plan within the query engine, and that result of the plan is transformed into an execution tree, and that's what gets executed. So once the plan is executed, if you're using the index, we request the index service for a scan request. We push down the filters. Index does its magic, gets you back the qualified document keys. And then if required, we go into the data service to fetch the relevant data, fetch the documents, then do the additional filters and joins. For joins, when we require additional data, we go back to the data service, get the data, do the join, aggregate, sort, and finally paginate before we send the results to the application. Right? This whole process, after we get the query in the query service, what index to create, what index filters to push down, what to do after we get the qualified index keys. There are many decisions that has to be done. These decisions are done by the optimizer. Right? Let's look at a little bit detailed view of how the queries are executed. Here in this diagram, you see some of the blocks is single blocks like the parse and the plan. There are other phases where we have multiple blocks. The main difference is when you see a single block, these actions are serialized. They happen in a serial fashion. The scan, the fetch, joins can happen in parallel as well. The max parallelism parameter controls whether we do an operation in operation serially or in parallel. The fetch operation is always in parallel by default. Okay. So in this process, we have the prepare phase. That's where the parsing and the planning happens, and then you run the actual query, and then finally you project the result set. Planning is the focus of this talk, and the reason I'm highlighting the prepare phase and the run phase separately is one of the optimizations you can do to improve your performance is to prepare the query once and then execute the query multiple times by binding different values to the query parameters. So this saves valuable time that we take in preparing the actual plan. Some of the simple queries take a couple of milliseconds to execute. Some of the complex queries, when you have a lot of choices, can take tens of milliseconds to prepare. So by preparing the plan once and executing the query multiple times, you save the valuable time for each subsequent execution. OK, let's take a deeper look into what the planner does. Each query that you submit can be executed in many, many ways. There are many ways to skin the cat. For each query, optimizer has to decide the access path for each of the key spaces that you have specified in the from clause. Once it decides the indices to use, it has to decide which filters has to be pushed down for each of the indices that are getting executed. Once that is determined, we have to determine the join order of the key spaces that you have joined in your from clause. Once all these are determined, it has to create the execution tree for the whole query. Right? Then for each key space, we talked about selecting the index. So depending on the predicates, depending on the indices that you have created, there will be many indices in your database. So we have to choose one or more appropriate indices for that particular key space. We use a rule-based optimizer. So we choose the index based on the keys that you have used, as well as the covering aspect of the query. We'll discuss the covering index and covered query later in the talk. So eventually, we select one or more indices for each key space, then match the filters with the filters that are in the query with the predicates that you can use while you create the index. Couchbase indices can be created. Couchbase indices have keys as well as the where condition that helps you create the partial indices. So we have to match both the partial predicate that you have attached to the index as well as the index keys as well. So once we decide which indices are appropriate for each key space, then we try to choose an index that can answer your query completely without having to go to the data nodes. If an index has all the data that is required to answer your query, we prefer that index. And once that is chosen, whatever filters that we need to apply, post-scan, post-join, those are created as well. So all this forms the input finally to create the execution tree. Okay. So now that we have talked about how it works, let's look at actual indices as well as queries and their plans. Right. So let's take a look at this query in this index and the query in detail. We are creating an index TSC ID on travel sample. There are two keys to this index, country and ID. Okay, those country is the first key, ID is the second key. We create a standard B-tree index, so the order of the keys is quite important. And then the predicate to the index itself is the type equals airline. So this is where, even though you are creating the index on the travel sample bucket, only the documents which contain this type field and the content of the type field is airline is indexed in this index. So when you have an index like this, we first look for the predicate type equals airline within your query to select this index as one of the options for the plan. Let's look at the query here. Query has got type equals airline, so that there is a match. We don't require a perfect match. The predicate in the query has to be a subset of the of the condition in the create index. For example, if the where clause had some value less than 10, okay, and the query had value equals 5, that's perfectly acceptable. We just need a subset we just need a subset of the predicate in the query. And then we have two more predicates, country equals United States and ID between 10 and 100. The second criteria to choose an index is the query has to use first n keys of the index. So this index has got 2 keys. In this query, we are using both the keys. That's perfectly fine. This index gets qualified. If you just use country, even then it is fine. It is the first key. That's perfectly fine. On the other hand, if you just used ID and you didn't have country equals United States, this index cannot be used because you're using the second. Even though the where predicate on the index matches, the key is not the first n key. It's the second key. You cannot skip over, right? It can be first one, first two. That's perfectly fine. But we have to have a predicate that matches one of the first 10 keys of the index. Okay. So let's look at the query plan that comes up. So we have chosen the index TSC ID for this, and because the index has the complete data. If you see the projection list of the select statement, we are just projecting country and ID for this. So the index has got all the information that we need for the query. So that's why whenever an index completely has the data that the query needs, you see the additional information in the explain called cover. That means this index covers the complete query. The additional thing you observe is cover meta TF ID. Meta ID represents the document key of the actual document. So every index entry has a pointer to the document key. So if your query is accessing meta ID, it's already covered. And then the filter covers, that's the where clause on the index has a match, so that's the covers. And then if you look down a little bit, you see a field called spans. Spans represent the index filters that we are pushing down to the index scan. In this case, we are able to push down both the predicates, country and ID. So this spans contains one or more ranges. In this case, it's one range with 2 values. So the first key is the United States, second key is the first key is the country, second key is the ID. That's represented by actual values United States and ID. That's pushed down to the index, right? This is the core of the query plan that represented by the result of your explain. So the last couple of things I would say is, because the order by follows the same order as the index keys, right? Order by country comma ID is in the same order as the index key, country comma ID, and we are using this index to fetch the data, we can avoid the sorting of the data altogether, right? So we follow the result that is expected follows the index order, so we'll eliminate the order by phase as well, because it's the best optimization technique is to do no work at all. So in this case, we have the pre-sorted data, so we just fetch the data as well. And then finally, offset and limit. So if you see the middle of the query plan, there is a field called limit 5 plus 10. This is where we are telling the index, I'm only interested in the 15 documents that qualify for this predicate. That's why it's 5 plus 10. We are not optimizing for offset yet. So in a release coming up, we will optimize for offset as well. Right now, indexer gives us the sum of limit and offset, and query engine ignores the first offset documents and returns the final result. Right? This is the crux of the basic optimization done for nickel. We'll go through various cases, especially because we started late. I may have to go a little bit quickly over the other slides. But if you understood this model, how we match the index, how we decide on each of the index key push down and the predicate push down, so you'll be able to see for your query how the explain looks, and then see if there's a match. If you have a predicate that doesn't get pushed in this range, that means indexer is doing more work than it should have. You should look at your index design, or your whether the predicates is right. Have you skipped any of the keys? Those are all pretty important things. And our engineer Sitaram has written a beautiful 30-page article that's on dzone that goes through every step in laborious detail with working examples. So that's another thing to look at as well. Okay, so now we looked at the covered index, and we have the same query, but we simply added the name into the projection list. So in this case, index has all the data to do the predicate evaluation, but it doesn't have all the data to give you the result. That's why you see the cover modifier is missing. We still select the same index, push down the same predicate, but eventually we have to go and get the data from the data service. Okay? So when you have a query that is completely covered by an index, we simply create the plan, go to the index service, get the results back, and return the result back to the application. So the query doesn't have to go to the data service at all. And the corollary is true as well. When you have a query that uses the use keys modifier to the key space, you can simply go to the data service, fetch the data, do the query processing. So whether we use the index service or the data service depends on what query you have given. So optimizer decides that automatically for you. When the query is not covered, you do see this additional operator called the fetch operator that I mentioned earlier. That fetch operation always happens in parallel. Once we fetch the data, then we apply the predicates again. So this is another important thing to remember. If it's a query is completely covered query, we get the results back from the index and project the results. If we have to go to the data service, we fetch the data and apply the predicates again, because in Couchbase, the index is maintained asynchronously. That means index is a little bit behind the data. So between the time we fetch the data from the index and we fetch the data from the query service, there could be modification to the data. So we apply the predicates again to ensure you do not get any data that is that doesn't qualify your predicates. Okay. Another access method that we can use is when there are multiple predicates and multiple indices qualify. When we don't have a composite index that covers the whole query, we can use multiple indices to filter out to apply the predicates, and then we do the intersection of the results from each of the index scans, and then do the follow-up processing. That's when you see the intersect scan in your predicate. In 4.5, we introduced a new type of index called the array index. It indexes the individual elements of an array. So it can index individual elements of a simple scalar array or individual elements of an array of objects. It can index individual elements of arrays of arrays of arrays of objects, whatever combination that you have. It's very flexible. I've shown the simplest example here. In this case, I'm indexing just the day attribute of an object inside the schedule. So once you create an index, then all the array predicates have array predicates any or any and every and within and so forth. In this case, I have used any v in schedule satisfies v dot day in 1 or 2. So you see the explain plan here. We choose the distinct scan because the index entries on arrays, because all the actual values are pointing to the same document, we want to get a distinct document out of it. That's why we call it a distinct scan. And you can see for this index scan, we push 2 separate filters or 2 separate ranges in the spans. First range is 1 to 1, second range is 2 to 2. That's how the in-clause predicates are pushed down as distinct ranges. And we use this plan as well. Okay. Sometimes when you count, you want the count to be as fast as possible, or you want the count to be as fast as possible every time, right? Prior to 4.5, when you had a count, we used to fetch the data from the index and do the counting within query service. In 4.5, indexer has implemented the counting method. So whenever you have a count and the predicates completely can be pushed down to the index, indexer can do the final count. We use a method called index count scan. We push down the count processing to the index, and we simply get the answer back. So this improves the performance significantly when you just have a count.
I have a question.
Can we hold the question to the end? Okay. Please, I want to answer all the questions, but since we started late, I want to complete it. Yes. Next is your join and nest and unnest processing. All the join operators, inner join, left outer join, nest, unnest in your from clause have to be understood, and we have to plan the access plan for this join operations as well. In this case, the query is doing a left join between the routes and airlines, and this, when you see the query plan for a join, for the left key space, that means the first key space, the travel sample alias to R, has a predicate, has an array predicate with any v in R dot schedule satisfies v dot day equals 1. This predicate can be pushed down to the index tx rax1. Observe here, the where predicate has got only the predicate on type equals route. That's the same predicate when you have on the index as well. And the second predicate is only matched to the first key of the index, right? We don't need the query to have all the keys to the index, just the first or the first n keys. So here it happens to be an array predicate that gets pushed down to the index scan, and then down in the query plan, you will see a join operator which tells you what keys from the R are joined with the key space A. And because it's a left outer join, so there is a field called outer, and that will be true. Okay. Even in join query, whether it's inner join or left join, we can use the index efficiently. If all the references to that particular key space have been used in the index keys, it happens to be true in this case, we can use the index to fetch all the relevant data for that key space, and the other key space, for the other key space, if we have to fetch the data from the data, that's perfectly fine. So we can use a combination of covering access for one key space and data access for the other key space. We can do all this combination. Essentially, right, essentially, the whole goal of optimizer is to do as less work as possible so that the query execution is efficient to give you the results back faster and use less resources on your system. So covering index path is very efficient, so we prefer that and use that wherever possible. Okay. Next, I'm going to talk about index join. So when you simply have relationships with child to parent or parent to child, right? For example, if you have, in this case, I have breweries and beers. I can, and each beer has a pointer to the brewery. In nickel, you always start with the child and do the join with the parent, right? So normally I should have started with beer that has a pointer to the brewery, and I can do the join. But what happens is, if you have a predicate on the parent, in this case, there's a predicate on brewery.state, you won't be able to join using the normal inner join syntax. That's why we introduce a new kind of join, which we call the index join. Here, instead of starting from the child, you start from the parent. In this case, you start with the brewery, and that has a predicate on states, right? We are only interested in breweries that are in California. Okay, we apply the predicate using the index, get the qualified documents in the brewery, and then we know the brewery ID from this brewery should point to should actually have a relationship with the beer documents. But the relationship is done through this beer.brewery ID clause. So using the index, we discover the child document and do the join, right? So this is how in nickel you can join from parent to child instead of the normal child to parent join. Okay. So when you have such a query joining from child to parent, the explain plan has a section, explain plan. That means the optimizer chooses a new operator called the index join, and you do need to create an index on the key representing the relationship between the child to the parent, and that index is chosen to do a second index scan in the within the plan. And even the query that has a join from the parent to child, if the index covers index covers all of the references to the document, we use a covering index path so that it's optimized for performance as well. And that's true for covering index is used for left join. We don't support the right join. What we mean here by right is when the relationship is on the right side of the join, we can use the covering index as well. After all the index scan, subsequent operations in terms of aggregation is pretty straightforward. For the aggregation, there's not too much to optimize except the count optimization I mentioned earlier. These are for informational purpose. For the aggregation, you will see the sections on initial group, intermediate group, where we iterate over the objects qualified for the group and create a final group. That's the final aggregate value that we represent. Then, you should try to avoid the sort by creating the appropriate indices so that we can exploit the index order. If there is no qualifying index, you will see the section with the order operator. This is where we actually sort the document. we sort the qualified documents and then apply the pagination in terms of the offset and limit if the index has not already done it. Okay. After all this, we finally project the data. After all this work, you get the result that you want, right? Those are all the different phases of how the query plan is done, how the query is executed. Okay. Now, I'll talk about how some of the decisions are made. You know, for each step, there is a decision to be made within the optimizer. So how we do the decision. So as I mentioned earlier, we are still using the rule-based optimizer. And I remember Don Chamberlain was also a co-author of the first cost-based optimizer paper. He's the co-inventor. So again, glad to have him here. So index cost-based optimizer is something in our roadmap. The indices chosen by Nickel query service are the ones that satisfy the query predicates. And when you have a complex query, we optimize each of the query blocks separately and then stitch them together to create the big plan. If you have a subquery, correlated subquery, that's not a separate block. That's already in the kind of in the parent block. But if you have subqueries in the from clause and so forth, or if you have queries that are put together by set operators like union, union all, and all that, each of them are planned separately. If the query contains use keys, that means we are not using any index at all, right? If no index are qualified, we use the primary scan, right? Primary scans are probably good to have when you're developing. You want to play with the queries. You want to understand what the results are coming in. That's all fine and good. In Couchbase, primary indexes are not mandatory. So in production, you want to avoid somebody doing a full table scan, right? So not having a primary index is a good way to avoid some of the disaster queries. Somebody is going to run a query without a predicate. It runs forever on your millions of documents. So that's a good tip there. Once the queries, once we select subset of the indices in our search space, we prefer covering index scan. That means you saw the examples earlier. If the index can answer the query completely, we prefer that. Otherwise, we choose the index with the longest satisfying keys. That means if you have multiple indices, if multiple indices are qualified for a particular query, we choose the index with the longest number of keys that are used by the query. And if there are multiple indices that satisfy, we can use the intersect scan as well. For unnest, we choose the array index. The array index key has to be the first key of the index. That's one of the requirements for the unnest operation, because the predicate is directly on the array that you are unnesting. Yeah, if none of these are available, we use a regular primary scan. If you have a primary index, if you don't have any access path, then we bail out and give you the error saying that you need at least a primary index to execute the query. Yeah, if the primary index is, we finally give the error. Okay, I said that. Primary index only contains the meta ID, that means the document key. So if your query is only accessing the document key, it's covered primary scan, so there is nothing else we need to access, so we just use the primary scan. And for any queries that don't have any other predicates, we access, we do the primary scan and then go and get the data from the bucket. In terms of index selection, obviously you're running a production system, online system. You could have many indexes that are that are online. That means indexes are completely built, and when they are online, the data changes are streaming to the indexer. Indexer are completely getting updated. In the middle of your production, if you are building an index, so they have not come online yet, or for any reason the index is disabled, the query engine ignores those indexes from creating the plan. If you have used a useIndex clause, we use that as a starting point for our optimizer, right? So as I mentioned earlier, we are still a rule-based optimizer. So we don't know the selectivities of the predicates that we are applying. Sometimes, if you know a better index, you can suggest these are the indexes the query should use. So we respect and obey the useIndex clause before we apply the rest of the rules. And the indexes chosen are have to have. Are we up the time now? 5 more. So indexes chosen have to have keys that qualify the query predicate, and we always choose the longest index, satisfying index. Yeah, covering index means the index can answer all of your, has all the data to answer your query. Regular index has subset of the data, and we still have to go to the data service to get the data. And unnest uses the array index, and for index count scan, we push the complete predicates as well as counting step to the index scan itself. Okay. This is one of the common questions that we get. When you have an index created with multiple keys, when you use and predicate on each of the keys, the query, you use the index, everything is fine. But when they use the or predicate, this index is not chosen, right? That's because when you have an or predicate, we can't use this index because index we go. That's why I mentioned you have to have the leading n keys. So if we don't have a predicate on the leading key, we can't have a predicate. We can't use the index to search on the second key. So for the or predicates, we can't use that BT index. We can use multiple indices, right, for each of the predicate, but not just one composite index if you have or predicate. Okay, here's an example of for a given index, what kind of predicates are used here, what can be pushed down to this index, what predicates cannot be used. I won't go into detail, but you can take a look at your leisure. These are the index, yes, query is the interface to the application, but to run a query efficiently and to meet your SLAs, you have to design the right indexes, and we maximize use of all the indexing features to come up with the best possible plan, right? We push as many predicates as possible to the index, and we exploit the index order to avoid the order by. We push the limit and the offset to the index. And the other optimization we have done is, when a index cannot be used to evaluate your order by clause, you could have millions of rows returning from your query, but you're only interested in the top 100, top 1,000, or offset 1,000, top 100. We don't get your millions of documents and do the sort and give you the top one. We only keep the top 64,000 documents. As the data gets streamed in, we do the automatic comparison of the top 64,000 documents, keep only top 64,000 documents, and then do the final pagination. That's another optimization done as well. Just like count, if you have a min clause in your statement, we push down that to the index as well. Min is basically a covering index scan with a limit 1. If you have duplicate indices, that means duplicate indices are two indices with everything exactly same except the name. Right? We automatically discover duplicate indices and use that as well, and use indexes to help you to determine indices when the automatic selection is not correct. Okay. So I think I talked about this in the previous slide, so I won't go into the detail in the interest of time. Let me see. Yeah, there are a few important things that we have changed in 4.6. That was the beta of 4.6 was just announced today. The first query is quite interesting. If you have an index that has that is on country, comma ID, where type equals airline, your order by clause in this query contains only order by ID. That's the second key, not the first key. Right? But the first key happens to be an equality predicate. Right? We have done a bit of an optimization in there to say, hey, if the first predicate to the index is the equality predicate, then we are already going to get the results in the order of the country and ID, so we don't need to get all the data and sort. So we automatically recognize this and exploit the index order as well. In 4.5, you have to give the country, comma ID explicitly to exploit the index order. We still don't have the index ability to create the index ascending and descending explicitly, but all our index keys can take expressions, right? We call it functional indices. You can have an upper, lower. In addition to that, you can also have arithmetic expressions like this, right? You can index this in this case descending order. The indexer thinks it's still creating the index in the ascending order, but you are negating the value of the ID. So you can play around with this order to get the order that you want. Okay, so yeah, limit when it is. We try to push when we can. Otherwise, we try to do the post processing. Okay. Yeah, this is an example of a query that where the count can be completely pushed down to the index scan. So the predicates completely qualify for the index, and the projection only has count, right? The requirement to push the count to the index is projection needs to have only the count. Okay. Min optimization, as I mentioned earlier, it's again a covered query with a limit 1. So that's how you push the min to the index scan. Yeah. So during query optimization, if there are multiple identical queries, we choose one of the indexes for the planning purposes. At runtime, we automatically do the load distribution to each of the indexes. The indexer client that is embedded in the query service does the load balancing automatically for you. There's nothing for the application to do. Okay, that's the end of my talk. I know we may have run over time by a few minutes. I can answer any question. Please go ahead.
I noticed that when you write the index, right, you have the where clause.
Mm-hmm.
It's basically you try to build a cover for it. Is that the purpose?
Okay, so the question was, you had an index with a where clause, but you're trying to build a covered query. I look at those indices with where clause similar to index partitioning in a relational database system, right? In relational database systems, you can create an index partitioned by some ID with different ranges. Here, you have to build this manually. There are two things. One is the partitioning of the data. Second is in Couchbase, all the data is in a single bucket. You have the type discriminator to differentiate between the different collections or different key spaces. So if you have an airline key space versus route key space, everything has a type discriminator called type. So that's another way to do it.
But my second question is, if you do it that way, right, this means you have to build multiple indexes I may have a type into
Yes.
airline, I may have the type into
The question is,
so
yeah.
during the update process, would that prolong the commit actually?
Okay. So the question is, that means you do have to build multiple indices in the in the same bucket. Yes, I mean it's almost like if you have multiple tables, you create different indices for each of the tables. It's perfectly fine to create multiple indices on the same bucket.
But would that increase the
Update time. I mean, every index adds to update time, but remember in Couchbase, indices are maintained asynchronously. It doesn't affect your write times to the bucket, and your write process will not suffer any additional latency. Once you update the data bucket, that gets streamed into the indexer, and indexer gets updated. Okay.